Can everybody hear me at the back? All right, welcome. I'm glad you're here instead of partying outside. My name is Rama Karve. I am a software engineer at Facebook. I'm in our Seattle office. I've been at Facebook for about 2 years now. And for most of that time, I've been working on some part of the videos experience, most recently focused on Playback on Android. So if you went to your Facebook feed, let's say about a year and a half ago, this is what you would see. So notice all of the spinners. It's not super obvious in this video, but scrolling was pretty laggy. Even when you clicked on a particular video, you had to wait a bunch of time for that video to start. In general, a pretty frustrating experience. The other thing we realized is that we needed videos to start really quickly when they were autoplaying, because otherwise most people would just scroll away and they would lose the opportunity to see a video that they may have liked. And so essentially we declared war on spinners. And this across all of our interfaces, Android, iOS, as well as the web. When we started this journey, we were not sure how this would actually pan out on Android with the diverse set of phones as well as network conditions that we had to deal with. But nevertheless, we were up for the challenge to improve this playback experience. So the first thing, as we started to attack the problem, the question was, well, how do we know we have succeeded? We needed some kind of metric that would allow us to, that would tell us where we were in our phase of improvement. And we realized that we needed a metric that was, one, easy to understand, pretty easy to explain, and it needed to characterize two things. One is how often do we play videos without any errors? There's no decoding errors, or we didn't fetch the video data or things like that. And secondly, we also needed to characterize how often people looked at the spinner, lost interest, and scrolled away or canceled playback. And so we did a whole bunch of brainstorming and came up with this simple formula, which we call playback success rate, or PSR. So the way I would state it is, out of all of the videos that were requested to play, either because autoplay was on for that particular device, or because somebody just clicked on a video that they wanted to watch. So out of all of those videos that were requested, how many actually started to play within n seconds? And the bar that we settled on was 1 second. So we wanted as many videos as possible to start playing within 1 second of when they were requested. So the cool part about this is that, as I said, it encapsulates videos, or videos that did not start at all counts against this metric, and also videos that were canceled, where the play was requested but somebody scrolled away before it even started. Both of these things are encapsulated in this metric. The other thing that we realized about this, which actually took us a little while to figure out, was that there's two ways of moving this metric up and into the right. One is you make videos start quickly, which would increase the numerator. But it was also important when we realized that, especially when we are auto-playing videos, if there is no chance that we can actually play that video quickly and well, there was really no point in trying to autoplay it. Autoplaying it would result in a worse experience than if we just showed the cover image and let the user make the decision on whether they wanted to watch that particular video or not. So this is what we came up with. After about a year of chugging away on this problem, this is what we have today. So as you can notice, not as many spinners, it's smoother, it's what I like to call closer to a Harry Potter experience, where it looks less like a video and more like moving pictures, which is kind of where we wanted to go with this. So next we come to the how. How did we actually accomplish what we set out to do? What were kind of areas of optimization that we were able to figure out? So before I jump into the optimizations themselves, I wanted to spend some time talking about kind of the overall architecture of videos on the Facebook app. So the main driver is essentially the surface you're on. It may be your news feed, it may be your profile or timeline, which is typically going to be some list of items that you scroll through. If one of those items happens to be a video story, we initialize a video component for it. Now, note this is not exactly what we call this stuff in code, but this is logically what we're doing. This video component is the thing that manages the UI around videos. It figures out, when to show the cover image, when to show the controls which only show up when the video is in full screen. They don't show up when they're inline. So all of those decisions are made by this video component. The other interesting thing that it does is it also figures out when the video is to be muted versus not, and it manages the surface that the video will be played on. The third thing it does, it drives a video player controller. The video player controller itself manages the life cycle of the video. It knows when the video has finished playing, when it's paused, when it's buffering, and will send a lot of these state transitions up the chain so that the UI, for example, can respond to it. The video player control, so back when we started this journey, we were using Media Player, which is the stock player available on Android. And last but not the least, we have a on-device cache that we use to fetch video data and cache it to disk. This is so that every time you scroll on and off a video, or go from full screen, or go to full screen or back in line, you don't have to go fetch video data all over again from the network. So this is what we started with, kind of, sort of. The next thing, so we knew from the beginning that one of the biggest things that we wanted to change with our architecture was to look into Exoplayer. Exoplayer is a open source library made available by Google. The reason we wanted to look at this library were twofold. One, it has support for streaming protocols like Dash. Until then, we were only playing MP4s, progressive download MP4s. And streaming is important to us because it allows us to do adaptive bit rates depending on network conditions, which we need. So that was the first reason. The second reason was that Exoplayer allows us to tune it, or tune the playback experience for whatever was important to us. And so since playback starts were important to us, we could tune it differently than otherwise. By contrast, Media Player was mostly a black box. So in kind of anecdotal tests, and which we proved out later with A/B tests, we found that Exoplayer was quicker to prepare. Preparation is the process that most players go through, where they parse whatever metadata is in the video, like the move atom for MP4s or whatever manifest exists, parses that and gets the player ready to play audio-video frames. And so we found that it prepared quickly. We found that it was more data efficient. All in all, it was a great option, and it turned out to be an enabler for a lot of the other optimizations that we made. And so, great, we put in an Exoplayer controller, which drove Exoplayer. Why did we need both of them, Media Player as well as Exoplayer at one time? One, Exoplayer is not supported on all OS versions. And secondly, we wanted to be able to A/B test and prove that Exoplayer was actually a better performing option for us. So it's great. We implemented this Exoplayer controller. We're ready to roll out. But the one thing that stopped us was that Exoplayer is more likely to cause native crashes in libstagefried. Libstagefried is the actual library a native library that does encode decodes on Android. And so Exoplayer, the crash rate was to a point where it really wasn't acceptable to us. So bummer. We spent some time trying to figure out, maybe we were just using the library wrong, and we could figure out why it was crashing and fix it. And so we did land some fixes, which allowed us to, I think, roll out to Lollipop at least, but KitKat and lower OS versions was still a no-go. And so we needed, some sort of plan B, some sort of other solution that would allow us to mitigate the crash rates that we were seeing. And so the idea we came up with was to move all of the Exoplayer processing to a different process. So that meant that if libstagefried got a crash, this other process would crash. It would signal an error to the main Facebook app, but the main Facebook app itself would not crash, which is a pretty bad experience. Instead, we would maybe not be able to play a couple of videos while we got the other process to restart and stuff like that, but that was still much more preferable than having a high crash rate for us. So one of the other really, really awesome side effects of this was that we ended up moving a lot of the video processing off of the main thread in our main Facebook app, which meant that scrolling was much more smoother, and we were just generally in a much more performance state in terms of the UI as a result of this change. So this was kind of like Exoplayer and what we call Video Player Service were kind of the foundational changes that we made that enabled some of the optimizations that we made alongside. And Marek is going to talk about them.
So hello everyone, I'm Marek. I'm working with Rama, and actually I was working on... Can you hear me? Okay, I should be good to go right now. So hey, I'm Marek. I'm working with Rama, and I was working on some of these optimizations. What can be interesting is that I work both for iOS and Android at the same time. So during my presentation, sometimes I will compare while I'm describing all of these optimizations, what were the difference between platforms. What is actually, let's start with more fundamental question. I mean, what is so difficult that Facebook is doing that others are not doing? The main difference is how we are using player. For majority of applications, it's just, okay, I'm clicking to play, and I'm waiting for spinner, I'm playing, and I'm good. What Facebook is doing is that we're living in the newsfeed. That means that when I'm clicking, the user tolerance for spinner is much, much lower. That's the first brutal fact. The other one is that user can do whatever. He can scroll away while I'm trying to play, and I shouldn't influence scrolling performance. That means that this is much more demanding for our footprint on UI thread. More than that, if we're trying to optimize metric that Rama mentioned for our play success rate, some of these optimizations will go against. For example, if I would like to just prepare a video that is just below the screen or just above the screen, that will consume CPU power. That's what makes this task a little bit more difficult. And I more or less simplified what is going on. As you see, there is no number above. It's because it's the effect of optimizations, and even this breakdown is different between devices and between network conditions. in essence, we can go, well, I won't show you, but I will describe you. We'll go like this. So we're starting with, at the very initial stage, with basically rendering what is in the screen. At this moment, we're checking, okay, should we autoplay this video or not? Let's say that we said, yes, we should play. We're building player at this stage. It takes a little bit of time in UI thread. After some time, player is getting ready and is asking for data. We can either take this data from our cache, or we can take this from the network. First, for some of these network requests, we also need to prime CDN, which means our CDN needs to request data from Facebook, and we need to send this to CDN. We're starting to getting data, which consists of Atom at the very beginning, then data itself. We're starting to extract, decode the video, and at some point, player says, okay, I have enough data to start playing. We're passing surface to the player, we start playing. So this is how we look like if we take just regular click-to-play player and put this into this autoplay condition. So let's try killing these elements one by one. Yep. Okay, so the first win is we did this for MP4. So how about if we go with frag MP4? Basically, this Atom compress. So Atom, if you're not familiar, is this index at the very beginning of your video that is basically saying, okay, so what kind of byte offset I should go to minute number 3 and 0 seconds. It's small for small files, but it's getting bigger as we're talking about longer videos. For example, for 25-minute video, it can be just 1 megabyte. 1 megabyte you have to download before you start even to play a single frame, before you start fetching data. With fragmented MP4, we are operating on like two-stage index that is for the fragments itself, but also for the first fragment. That means that this Atom from 1 megabyte for this big, long movie can be compressed to under 50 kilobytes. Let's go forward. Next optimization is with a trade-off. If we see that user is in not very good network, we can try to compress data, because what actually frag MP4 can enable us, if it's built on top of Dash, is to introduce adaptive bitrate. Basically, we can guess in what bitrate we should play the video for user to have the best experience. Again, we can answer this question with A/B testing. This is trade-off, however, because the lower quality, I mean, if I'm in very fast network, probably that's not something I would like to experience. So we need to be very cautious about it. We also need to have very good guess about the quality of the network that the user is in. Now let's go also one step further. Let's just throw this away from critical path. And we're going into prefetch. And this technique, while very successful, has very serious drawbacks. So as you see, we can achieve tremendous optimization here. However, prefetch for video is augmenting all problems for regular prefetch for any other data and is introducing new ones. Prefetch, as name indicates, we are fetching data, but are we going to use it? We don't know. We may actually fetch this for users that are on very, data conscious plans and never use it. So this is this technique needs to be very much tuned up for specific user, whether he's in Wi-Fi, whether he's in cell. What is our guess about user data plan? Another problem is that, remember, we're still in feed, we can do whatever. I mean, this prefetch can collide, for example, with images or whatever else we are fetching. So again, this can be a little bit mitigated by very cautious network prioritization. But again, something that you need to keep in mind, this optimization can be very easy to backfire on you unless you know what you're doing, unless you're slicing in the data and you're optimizing for specific cases. Now, yes, so we are doing this prefetch, but this prefetch we may need more time that actually is needed to finish prefetch, and then we start, so basically we can start playing before prefetch is completed. So we need to try to fetch as little data as possible. Because we have luxury to know about practically everything about this video. We know the atom size, we know how many bytes. We can pretty much guess how much data is needed to fetch to play for 2 seconds. And we can guess from network condition that 2 seconds is enough to re-establish connection for the user and request more data. So basically there won't be spinner after 2 seconds. This is very dangerous scenario. If you just go with one metric, which is playback success ratio, we can optimize this metric, but at the same time fetch so little data over here that you stall your playback after 1 second. So you need to be very cautious, and you can't be tunnel blinding into just looking at one metric. One more natural extension is actually not doing this naively, and not like, let's say I'm doing prefetch, I'm starting playback, so I'm starting another network fetch. Rather, I'm intercepting prefetch network requests, and I'm passing this directly to the player. That is avoiding having 2 network requests. And this is something cool. This is what Rama a little bit mentioned, but this is probably the biggest magic in this whole presentation. We clone UI thread. Basically, we moved ExoPlayer into its own process. It has its own UI thread. All we need to pass is a surface to render. There are many benefits with that. You're basically not affecting main application UI thread, so you are getting better in scrolling. Your exceptions are, as Rama said, thrown into the separate process so that we can restart, and that can be even quite transparent to the user. However, this is great. There are some limitations with this technique. The limitations are 2. The first one, if we're talking about dual core devices, look how much stuff we're doing in this stage. We can easily saturate dual core devices. So throwing out of UI thread is not helping for these devices, because these 2 cores are already saturated, and whether you move this to another UI thread or not, you pretty much have crappy experience already. Second is actually, I will let you know about a little dirty secret that is allowing your phone to have decent battery life. You're opening your Facebook application or any other application, and you have 4-core device. You can think that CPU, okay, it's not sleeping anymore, it's active, right? You're wrong. 2 cores are active. The moment that we need another 2 cores, it's only when we are bringing them from suspension. That means we need to have dozens of milliseconds to bring up these cores. That means even for 4-core devices, something around this stage, we will basically need some time to bring up the other 2 cores from sleep to be able to use these 2 cores. And this is the moment when we can drop some frames, even with this optimization. Let's just look from a side, because right now we only discussed the scenario that we have 1 video. Now let's say we're going into some video-rich environment, let's say feed only consisting of videos or timeline consisting of videos. If you do your fetches naively, that's how your prefetches would look like. I mean, it doesn't make sense because they're competing with each other. That simple answer, it's with trade-off that is not visible, but if you see with a kind of high resolution, you will see a little bit space between these requests. This is round trip time, because the moment I'm finishing and requesting next prefetch, I'm paying this price of round trip. However, in general, it's still very, very positive. User, when we're opening the feed or opening the timeline, is starting at the very beginning. If we sort in this order, pretty much these prefetches will be arriving in the order that user is viewing. If he scrolls, that's what just happened, we can quickly reorder, because if we have only 1 or 2 concurrent prefetches at a time, it's very easy to dynamically reprioritize them, even if we don't have at our disposal network reprioritization, because there are two reprioritization. One, in your internal queue of prefetchers. Second, when requests are on wire. You can use throttling techniques to basically freeze prefetches that are no longer of high priority and fire different one. But let's take this even one step further. This is the scrolling scenario, but this is the scrolling scenario not from prefetch perspective, but from CPU perspective. What I did, I just scrolled quickly the feed. And we added logics to basically figure out that if I'm scrolling fast and I'm not going to land in screen for this video, I'm not even attempting to play. Positive result is not only in just optimizing our metric, this is much better scrolling experience. So this was high level, and well, we're waiting for your questions with Rama. So the question is if ExoPlayer is written in Java or C++, right?
The library itself is in Java. It's basically written on top of the media codec APIs, which are available as part of Android starting, I think I want to say Jelly Bean. I'm not sure about that. Yeah, it's 16, right? Can you repeat that?
I was decoding time for each frame. Is that level of implementation?
We haven't. So the question was, has decoding frames been a limitation? Not that we have observed.
So actually what we discover in profiling is that there are still some elements I haven't touched, but ExoPlayer is not very optimally written. There are still some huge areas for optimization, both in CPU usage and for concurrency. So these are much bigger problems than decoding. Just to give you an idea from like simple profiling, it's easy to see that the process of passing the frames to decoder and rendering is much less than extracting from the stream inside ExoPlayer. So this is one big inefficiency there.
I can't hear you.
You're rendering it into the process, right? And then you put the maps over IPC and creates one.
So we are passing basically the surface. So this process is not giving us back just frames to render. It's getting surface to render. It's as optimal as it's optimal in Android system. I can share with you, if you're interested, some links to describe how this passing buffers to render in Android system works. But basically, there is no extra cost. There is small cost for inter-process communication that I'm estimating to be less than 5 milliseconds.
Yeah. And so when we started down this path, that was one of kind of the big risks, that passing buffers across would probably not be efficient. And so the big question was, well, could we do this thing where we pass the surface to the process and just have it render? And it turned out like it's possible.
So practically no extra cost, and you are freeing up UI thread out of video rendering. That's the benefit.
So you basically have the surface attached to the separate process owned by ExoPlayer, and then you're doing a copy of the content of that surface object.
So we're passing the pointer to surface itself. Correct me wrong?
Yeah.
Yes. So basically the question is how we are just handling this. So there is no copy between processes. We're just passing the pointer to the surface, and the process is directly rendering to the surface itself.
Yeah. Good. The question is, how did we clone the UI thread? Unless you.
So every process has its own UI thread. Basically, the separation here of UI threads is possible because we are passing the surface just Surface is, you can imagine this memory region in which the other process renders. Then there is no collision between processes. They can render each one in its own thread. And this is like practically cloning UI thread from this perspective.
Yeah.
So the process fails the point. Do you like just stop trying to use catch up and just switch the video?
That's a good question. So the question is, if the video player process ever fails, do we ever fall back to using media player? We don't today. And it hasn't, so we made the call of just having the video fail to play back. But you know, that's one way, that's a good optimization that, that you could make.
In general, like if we fail to play, we are trying to recover in a way that is invisible to user. Quite frequently when we tested this, we couldn't say the difference when we crashed like 3 times and restarted because we introduced our crashes artificially versus playing immediately. So this is like, you know, good kind of indication that this isolation was quite good.
Any more? All right, thank you.
Thank you.
Oh. So the question is, when you prefetch, do you prefetch the whole video or parts of the video? Parts of each video.
So the answer to this is a good question. We are trying to prefetch atom plus n seconds. What is n value? I can tell you because basically we can figure this out based on network conditions. We basically need to prefetch as much time that is kind of compromise. It's enough time if we start play to establish connection and fetch the beginning of the rest of the video before we run out of data. So this is like, you know, what is pushing us from one side. From the other side, if we fetch too much, one is data usage penalty, but the other point is that basically we are less likely to finish other prefetches for other videos. So this is always a compromise based on user network and conditions. So I don't think, like, you know, I can discuss this because of some legal limitations, but basically we're doing, I can, like, you know, tell whatever you can figure out already. So we are basically, our application is doing network requests before that. We can have some estimation based, for example, how quickly these packets arrive to the device. Of course, this is just estimation because few requests are as big as the videos, and what we are basing on is in past. However, like, you know, we found this quite effective technique despite its drawbacks. Yes, however, in this aspect, so there was also, like, you know, comment that ExoPlayer can figure this out. However, the problem for us is that we're starting prefetches before we start playing a single video. So we need to figure out this from other sources.
All right, thank you. We'll hang out here for more questions if you have any. Thanks.